Chapter 12, Elementary Chemical Kinetics, Section 12.4, Activated Complex Theory. Activated complex theory, also known as transition state theory, states that between the reactants and products in an elementary reaction, there is often a transition state structure. The transition state has a higher energy than both the reactants and the products. The transition state structure resembles something between the reactant and the product. In the transition state structure, one or more bonds in the reactant are partially broken. One or more new bonds in the product are partially formed. Let's look at one example in this reaction. Fluorine reacts with HCl to form a chlorine atom and hydrogen fluoride. And between the reactants and the products, there is a transition state. In the transition state structure, we have fluorine-hydrogen partial bond. We have hydrogen-chlorine partial bond. If we look at this reaction path from left to right, so from the reactant to the transition state, we can see the fluorine-hydrogen partial bond is formed in the transition state. The hydrogen-chlorine bond is now partially broken in the transition state. And finally, in the product, we have a hydrogen-fluorine bond and an individual chlorine atom. Now, what's the difference between the activated complex and a transition state? So right here, we see this transition state at the top of the hill, right here. But an activated complex may adopt the transition state structure or a structure very close to that of a transition state. So somewhere here, okay, this reactant can form a transition state or something close to that and overcome the barrier to form the products. The activation energy of the reaction is the energy of the transition state minus the energy of the reactants, denoted by E sub A. This is the activation energy. It's the energy of the transition state minus the energy of the reactants. So it simply means the reactants must get some additional energy, this much, to overcome the barrier and form the products. We have the equation over here. Activated complex theory, also known as the transition state theory, states that between the reactants and products in an elementary reaction, there is often a transition state structure that resembles something between the reactant structure and the product structure. Here's another example. Let's look at one of the SN2 reaction. SN stands for nucleophilic substitution. SN2 means it's going to be bimolecular. Now let's look at this reaction. So from chloride and bromomethane to this chloromethane and bromide. In the middle, we have a transition state. So now let's look at the reactants. We have a chloride, we have bromomethane, okay? And let's look at the product. We have a bromide and a chloromethane. So in the middle, we have transition state structure that resembles something in between. Alright, now let's look at over here. The chlorine-carbon bond is now partially formed in the transition state. The carbon-bromine bond is partially broken in the transition state. So that's why you have two partial bonds in the transition state. One is carbon-bromine partial bonds. The other is carbon-chlorine partial bonds. And over here, well, the bond between carbon and bromine is completely broken. The carbon and chlorine bond is completely formed. And now you can see we have energy going up and then going down. This is not the entire potential energy surface for the reaction. You can see on the left hand side we have only 8 data points. On the right hand side we have only 8 data points. So very likely it should extend to like until it levels off, and this one should level off. Alright, and again after it levels off, we'll be able to get the energy of this reactant complex that consists of this bromomethane and chloride, and they should be relatively close to each other, solvated by water molecules. This is the beginning of the reaction, this is the end of the reaction, and this is in the middle between the reactants and the products. Again, the transition state has higher energy than the reactants, but also we need to remember the transition state structure has higher energy than the products. And also you can view this reaction from right to left. You can go from here, you have bromide reacting with chloromethane, form the transition state structure, and go back to over here with a chloride and bromomethane. In the vertical axis we have the energy of the three species: reactants, transition state, and product. But those are in a unit of Hartree. One Hartree is 2,600 kilojoule per mole, or 627 kilocal per mole. So even though you can see the energy difference looks small, well, you need to multiply that by 2,600 to convert it to kilojoule per mole. So the energy barrier is not that small. And the horizontal axis is called the intrinsic reaction coordinates. It's just a description about the changes in the structure of from the reactants to the transition state to the product.